Hello and welcome to yet another awesome stream on Church of Entropy live streams. I'm happy to be here, joined today by my guest Euler 2, who will be talking us through important aspects of quantum numbers. After which we'll be opening up the floor for your questions, so get them ready. His main topic of interest is mathematical philosophy. Looking forward to the presentation. Over to you, Euler.
Okay, awesome.
Hello,
Okay,
and
this is going to be
welcome.
fun. We're exploring a
Yet
completely
another
new
awesome
number system.
stream on Church of Entropy live streams. I'm happy to
Essentially,
be here, joined today by my
we're going to
guest,
look at a few
Euler 2,
results,
who will be talking us
and then
through
we're going to open it up to a more general
important
conversation afterwards
aspects of quantum
about
numbers.
maybe the utility of this sort of
We'll be
stuff,
opening up the
or just
floor
anything
for your
really.
questions,
Okay, so
get them ready.
let me just introduce it.
His main
The topic is quantum
topic of
numbers.
interest is
Okay,
mathematical philosophy.
and so you can kind of
Looking
think of it
forward
as
to the
like
presentation.
the regular
Over to
number
you, Euler.
system, but kind of on steroids. Okay, awesome. Okay, so let me just give you some examples. Okay, this is going to be fun. We're exploring a completely of course we have the natural numbers, things like 1, 2, and 3, right? So on. Look at a few results, and then but there are quantum versions of these numbers. Like we inject them with like quantum mechanics, and then they become more souped up. For example, the quantum 3, and I'm going to introduce some notation here. If I put brackets around something, that means it's the quantum version of that number. So the quantum version of 3 is going to be 1 plus q squared. Okay. Looks a little bit weird. Like, what are these q's? Well, these q's are going to be like energy, as we're going to see throughout the day. Essentially, the idea is, from the quantum version, we can recover back the normal version of the number. And we do it by plugging in q equals 1, right? And that's easy to see. If we plugged in q equals 1 into this expression, we'd get 1 plus 1 plus 1 squared, which is 3, okay? So the quantum version of the number is a generalization, a strict generalization of the regular number, because we can always recover back the regular number by plugging in q equals 1. Okay. What's the point though? Well, think about what numbers do. Numbers, well, they count the amount of things, usually. That's the most common usage of numbers. But there's something kind of deficient about that. If I were to count, well, let's see, the number of dots in this rectangle, well, there's 6 of them, that's easy. But there's more structure here, right? These aren't just like 6 dots in a bag all scattered around. These are 6 dots in a rectangle. There's more structure. If I were to just attribute the number 6 to this configuration, I'm losing information. And so the idea of the quantum version of the number is it retains more information that you can hold on to. Okay, let's have a look at that. So let's just do another example here. Let's do the quantum number of 5. And hopefully you'll be able to start to guess what the pattern is. Okay, 1 plus q squared plus q cubed plus q to the 4. Okay, and this makes sense as well. If we plugged in q equals 1, we'd get back 5. Okay, so it's all working. What's really interesting about this is when we multiply them. Let's try. Let's look at the quantum number 2. It's going to be 1 plus q. Okay. So let's do 3 times 2. 3 times 2. Okay, we can do that. We have 1 plus q squared times by 1 plus q. Okay. Okay, if you know your algebra, we should be able to expand this out. I'm going to do it in my head. See if I get it right. If I get it wrong, just correct me. I think it's going to be 1 plus 2q plus 2q squared plus q cubed. Okay. Which is definitely not 6. This is interesting. 2 times 3 is not equal to 6 in the quantum realm. Because what would 6 be? If we look at what 6 is, 6 would be this. That would be 6. And these two things are completely different. 2 times 3 is not equal to 6. That seems a bit silly. So maybe this is a stupid number system. Actually, no, it's not. 2 times 3 was never 6. Let's think about what 2 times 3 really means. Okay? If we had 3 dots, 2 times 3 means 2 lots of 3. So maybe we could draw it like this. There we go, 2 lots of 3. What does 6 mean? Well, it's 1 lot of 6. So if we draw them out as shapes, they are different shapes. The thing that they have in common is there's the same number of dots here, but they're different shapes, and hence they're different quantum numbers. Because quantum numbers have more information, they're preserving the structure as well. Okay. So I kind of got hooked as soon as I saw this. And what's lovely is you can ask basic stuff like, well, is there a quantum, I don't know, factorial? Is there a quantum derivative? Is there a quantum trigonometry functions? Is there quantum exponentials? And the answer to all of that is yes. It's weird. And they're all just better versions of the things we've already seen. So let's just look at a few examples. We're going to do, let's see. We're going to do quantum factorials. Just to remind people of factorials, if they haven't seen them in a while. A factorial, this is regular numbers, right? Because there's no square brackets here. A regular factorial is 3 times 2 times 1. So how this works is you start at your biggest number, and you keep subtracting 1 and multiply them all. Okay? In this case, it happens to be 6. Let's do 5 factorial. That would be 5 times 4 times 3 times 2 times 1. And what would that be? That'd be 120. Okay. So let's consider the quantum factorial. So, let's do the quantum version of 3 factorial. It's going to be 1 plus q squared. That's, sorry, q squared. That's the quantum 3. Times by the quantum 2, which is 1 plus q, times by the quantum 1, which is actually just 1. So if we do this, actually we did this one before. This was our calculation that we did before, so I can just cheat. Do this. Awesome. Okay. Who cares? Well, I care. I care a lot. Factorials count interesting things. Factorials count the number of permutations of a certain number of objects. For example, 3 factorial counts the number of ways to rearrange 3 objects. Okay, so let's have a look at that. If I had 3 objects, let's call them A, B, and C. Okay, I could put A on the left, B in the middle, C on the right. But there's more ways I could mix it up. Okay, I could have A, C, B. I could have B, A, C. I could have B, C, A. Okay, I could have C, A, B. And finally C, B, A. There are 6 ways to rearrange 3 objects. And that's exactly what 3 factorial calculates here. That's why it's 6. Okay, so what does quantum 3 calculate? Well, it's got to calculate permutations as well, but it's got to calculate them with more consideration. It's got to give us more information. So what it does is it calculates permutations, but it counts the number of swaps that you need to do in order to get those. For example, we don't need to do any swaps to get to this configuration. It's already in that configuration to start with. To get to the configuration ACB, we had to do 1 swap. And we can see that because we had to swap the B and the C around. Okay, let's see. From the starting configuration, how would we get to this configuration? Well, that's easy. We'll just swap A and B, and then we'll be straight there. So this is also 1. Okay. B, C, A. Let's have a think. So Yeah, this is going to be 2. Let's have a look. So if we start ABC, how do we get to BCA? Bear in mind, a swap, you have to swap two adjacent things. You can't just swap anything around. They have to be next to each other. So I could swap the B and the A around. One swap would get me this. And then I could swap the A and the C around. And that would get me that. Is that right? Yep, so that took 2 swaps to get there. Similarly, this takes 2 swaps. And this takes 3 swaps, if you check. Okay, who cares? I care. It's given us exactly this. Let's have a look how. This took 0 swaps. We're going to associate the number 1 to this. This took 1 swap. We're going to associate the number q to it. This took 1 swap, another q. 2 swaps, so this is q squared. This is q squared. And this is q cubed. And if we add them up, look what we get. 1 plus 2q plus 2q squared plus q cubed. Which is this. So, the quantum version of 3 factorial, it still counts
the
permutations.
coefficients? Sorry, I just want to be clear. Are you talking about that this process gives the coefficients the expansion?
100%, that's exactly what it does. So
just being clear, that's really impressive. Nice. Sorry for the interruption.
No. If you've got any questions or clarifications, because I've seen this 100 times at this point, please slow me down. Okay. So essentially, quantum 3 factorial, it counts permutations, but it counts them including how many swaps it took to get there. It's kind of weird. So we can see here, we have 2q, because we have a q and a q there. We have 2q squared, so we have a q squared and a q squared. And then we have 1q cubed there. And that's exactly the quantum version of 3 factorial. Okay, very strange. So what's going on with this Q business? Like, what is it? Well, you can kind of think of it as the number of interactions or like an energy. So let me just give you an analogy here. Let's go all the way back up. So here, I took this off the internet. This is a Feynman diagram, and it shows particles interacting. And you have these things here. This is a g squared, g to the 4, g to the 6. Okay. What is this? Well, it's counting the number of nodes. So there's been 2 interactions here. There was an interaction here, and there's an interaction here. And so it's come with a factor of g squared. Here there were 4 interactions, we can see them. 4 things where things were bumping into each other. And here there were 6 places where particles collided into each other. So when particles collide, you get a factor of g. And this is kind of the same thing that's happening here. We have like things interacting with each other, like swapping. That you can imagine that like they've bumped into each other and they had to pass by each other, but they interacted in order to do that. And so there was a factor of q that appeared here. Okay. This is just one example. I feel like I've been talking for a long time, maybe 10 minutes on this example. I'll do 2 more examples and then we might open it up. Okay, so next one, I want to do...
This might be a good time for me just to say real quick, if there's something that's not making sense, like I'm able to follow this and I'm riveted, but if anything technically isn't making sense, those in the audience, probably better to bring it up as it's happening so that it can be resolved. Not to this big question mark hanging over the whole thing.
Well.
Yeah. So
oh yeah, I want to ask a question.
Thank you.
How are these swaps analogous to interactions?
We have not got there yet. This is a proof of concept. I think that'll be a bigger question for later, maybe, eh?
Okay.
I don't know, or if you feel like you can answer this quickly now without derailing your example, go ahead. But yeah.
So it is just an analogy, okay? I can put it in context where it makes a lot more sense, but you can think of it quite literally as like these things are particles, and they have to pass through each other. They have to swap past each other, and in order to do so, they've had to interact. And whenever there's an interaction, you get a factor, a multiplicative factor. So how many interactions had to occur to get to this configuration? Well, 3. Now, it is an analogy, right? Because you could imagine, I don't know, maybe they swap back and forth 100 times and then got to this configuration. So shouldn't there be like a q to the 100 as well or something? Yeah, so this is just an analogy. How about we do one more then? And it's gonna be more closely related to the interaction thing. So have a look. So here's a standard problem in mathematics, okay? Let's think about it. We want to know the number of paths to get from this bottom left corner to this top right corner. Let's just draw a grid out. I'm going to count them. Okay. Now, of course, I'm not including paths that go backwards like this. When I say path, I'm talking shortest path. We can only go to the right and up. Okay, we don't want to be turning around. That'd be silly. Okay, so let's just count them quickly. We could go along here and up. That's 1. We could do this. We could do this. Oh, there's a lot. We could do this. So that's 1, 2, 3, 4. Okay, what else? We could go like this. Okay, this seems a bit of a mess. So is there a faster way to do this? Yeah, it turns out this is related to binomial coefficients. So let's just see how. How would we get to the top right corner? We would have to make 3 right moves and 2 up moves. And we can do them in any order, right? We could do a right move, then an up move, then a right move, then an up move, then a right move. But we know, in order to get to the top right corner, we have to do 3 rights and 1 up and 2 ups. Okay? So we could put it in a code like this. Right, right, up, right, right. Right, right, up, right, up. What would that look like? Right, right, up, right, up. And there we are. And it's quite a standard thing in mathematics to calculate this. I'll just spoil it. It turns out to be, and this is called a binomial coefficient, it's going to be 5 choose 2. And that's going to be 10. Okay. So this is called a binomial coefficient, and it's actually heavily related to factorials. This is going to be my second example. Of course, this is quite a standard thing in mathematics. You learn it maybe when you're like 17 in some courses. But we're about quantum numbers. We're going to consider the quantum generalization of this, because we know what this thing is counting. This thing is counting the total number of paths from the bottom left corner to the top right corner. And it's given us 10. There's 10 paths. Okay, but are all the paths equal? Well, definitely not. Maybe some are more energetic than other paths. Okay, so this is interesting. Let's just think what would be like a really low energy path. And this is just an analogy, right? But maybe if it goes along the bottom and then goes up. That's pretty sad. That's a pretty sad path. Okay, let's do a different path. I'll draw a new grid as well. Make it easier. How about this path? Let's do it. This path. How energetic is this path? Well, maybe we can count it like this. The number of blocks underneath the path. So I would say this path has energy 3. Okay. So we're going to have a bunch of different paths, and they're going to have a bunch of different energies. And it would be cool if there was a fast way to do this. And yeah, it's called the quantum coefficient. Actually, I've just thought of a better way to write this. How about this? Let's use square brackets. The quantum binomial coefficient. Okay. And if you've studied a bit of binomial coefficients, you'll know there's a fast formula for it. Let me just write it. 5 factorial over 2 factorial times 3 factorial. Okay, so we could take a guess, a conjecture. Turns out it's true. But the quantum binomial coefficient is the quantum 5 factorial over the quantum 2 factorial times by the quantum 3 factorial. Kind of bizarre. We can prove this, but we're not going to. It will take up too much time. So it's a faster way to count paths, including energy. And again, it's just strictly got more information. If I just cared about the number of paths and didn't care about the energies of the paths, I can plug in q equals 1, and I'll get the answer 10. This would be 10 if I plugged in q equals 1. But I don't want to plug in q equals 1. What we could do is we could explicitly calculate this. Just thinking to myself if I want to. No, I feel like that will get pretty dull. Has anyone got any questions about what exactly is going on here? Because I think it's kind of a little bit confusing.
I have a series of questions. It might take a while if you want to finish first, and then I can go through my questions. They're more the long, drawn-out, navel-gazy, pedantic questions we all love so much.
Yeah, we'll definitely have plenty of time for those type of questions. Okay. Okay, I want to do. Okay, so just to reiterate the point here, because hopefully I want people to get the point. The point is, binomial coefficients count the number of paths. I've just created a quantum version of the binomial coefficient, which counts more. It counts more. It does count all the paths, but it discriminates them because some paths have more energy than other paths. For example, this path here had energy 3. Where did I get the number 3 from? It was the number of blocks underneath the path. Let's do one more example. So actually, this path would have contributed a q cube factor. Let's do a different one. In fact, there's one other path of energy 3 as well. Let's do it. It would go like this. It would go up, all the way to the right, and then up. We look at the total number of blocks underneath it. That's the energy of the path. And this also is going to be a factor of q cubed. Okay. So what you can do is you could expand this out, because we technically know what this is. It's going to be a mess to write, right? Actually, I'm not going to write it. It's going to be too long. It's going to have so many factors of q, right? It's going to be a massive expression in terms of q, because imagine how big this is going to be. And then we're going to have to divide it by this. But it's going to cancel, and you're going to be left with a polynomial. And it's going to give you the total number of paths, including energies. Okay. I'll do one last one. This one's a bit more gentle. So if this one lost you, hopefully this one's going to make more sense. This is quantum Fibonacci numbers. Okay. I'll just remind you of regular Fibonacci numbers. They're absolutely great. Kind of a bit... mystic people love them. They look around at the universe and then spot the number of Fibonacci stuff in petals and flowers and pineapples.
It's another one of these self-referentially defined series, right?
That's right. So it's defined by a recursion. So let's see. So the first Fibonacci number is 1. The second Fibonacci number is 1. And then from this point onwards, you just add the two previous numbers. So 1 plus 1 is 2. 2 plus 1, add in the two previous numbers, is going to be 3. 2 plus 3 is 5. I'm just going to take a drink, see if you can figure out the rest in your head. Give me one sec.
That's really tough to monologue on these things. I can completely relate. So.
Yeah.
I'm going to go with 8.
I agree. 8, 13.
Are you ready to take back over?
Yeah, I am. Okay, so these are the regular Fibonacci numbers. Like I said, with everything, there is a generalization. There's a quantum generalization. The quantum Fibonacci numbers. Actually, they're not that special. It's really simple. In fact, we've already seen it before. I just want to explore it a little bit, though. Sorry. Let's take 5. What's the quantum version of 5? It's the quantum version of 5. There's nothing special about it. The quantum version of 5 is the quantum version of 5, and we already saw this before. It can be this. The reason why I want to explore it is there's a geometric way to understand Fibonacci numbers, and it's a way that people might not have seen before. Let's take 5, for example. In fact, this is how Fibonacci numbers were first discovered. it's related to poems. So there was some dude, I don't remember his name, he's probably Indian, and he's trying to find like the total number of poems. And in his poem structure, there's two things that he has. He has one word, like words with one syllable in, and he has words with two syllables in. So let's find the total number of poems with 4 syllables. Okay. Total number of poems with 4 syllables. We could have a 1 syllable, 1 syllable, 1 syllable, 1 syllable. We could have a 2 syllable, a 1 syllable, 1 syllable. We'd have 1 syllable, 2 syllable, 1 syllable. I'm not sure what type of poem this would be. Probably something like cat, sausage, cat, right? Do you know what I'm saying? That's 4 syllables, right? Sausage, yeah.
Mathematical decomposition of poems. Yep. Right there with you, man. Got you.
Right, and then I don't think the guy was a maths guy. He was just probably bored. There wasn't much to do back then. And then we have something like sausage at the end there. Okay, that's all poems of length 4. That's all of them. And how many are there? 5. That's not a coincidence. That's they're related to Fibonacci numbers. What about poems of length 5? This might be a bit of a pain. Well, there's going to be 8 of them. Do I want to go through all of them? Why not? Okay. Poems of length 5. There should be 8. Let's try and find them all. So we'll start easy. 1, 1, 1, 1. Of course, we'll do these. In fact, actually, this is quite easy. It's systematic. And you can make your own poem of these structures if you want. Okay, now we start to have ones with like this, like that, and maybe like this. Is that 8? Am I crazy? 1, 2, 3, 4, 5, 6, 7, 8. Yes, I was right. Okay, so Fibonacci numbers, they relate to poems, but we can maybe these poems have different energies. Would that be weird to like associate energies to poems? So this is how we're gonna do it. It's a little bit bizarre. This one has got energy 0. Okay, why? Because the energies are gonna come from these 2-syllable words. You can kind of think of them like particles if you want. So this would be like having 0 particles. This one is gonna have it has 1 particle, and it's in the lowest position it can be in. So it's gonna have energy 1. This one has 1 particle as well, but it's a bit more excited. So this is energy level 2. Why? Because this one starts in the 2nd position. Okay. This one has energy level 3. Because it's 1 particle, but it starts in the 3rd position. Okay. This one has energy level 4. That's good. Oh, wow. I think I coincidentally drew them in increasing energy order. That's awesome. Because let's look at this one. What would the energy of this one be? Let's think. This particle here has energy 1, because it starts in the 1st position. This one has energy... Am I crazy? Is this going wrong? Let me think.
My experience, doing derivations on the fly never works. I'm following, but in terms of the number crunching, I kind of have like I just don't do that on streams ever because it just never works.
Shouldn't it
Oh, yeah,
be?
I don't...
I think it should be 4.
Yeah, but that would bust my theory if it were. If it were 4, that would be sad.
Was this your theory of numbers, or
Yeah, this is mine.
Really good.
But
There may
it
not
was
be
right
more
when I
than
last
4
checked.
independent numbers, though. So long past 4 may be your thing. Just saying. Does appear to be a limit on independent numbers. Intrinsic limit.
Let's have a look. 0, 1, 2, 3, 4. Oh, okay. Okay, look, this is 5. Let's try and understand how we're getting to 5. Look, the whole point of mathematics, and this is a great demonstration because we're doing this on the fly, it's to kind of look at a system and try and generalize it and try and find more structure in it. Now, you don't want to be doing numerology, okay? And there's a point at which you can slip into that. You've got to find interesting structures which generalize and have utility. Okay? This is one that I came up with. Maybe it's bogus. I don't think it is. But I'm about to tell a story, and I could be telling a fake story. Just bear that in mind. But my claim is that this has energy level 5. Someone in the chat said, doesn't have energy level 4. It does, but then that would be a disappointment because that would break my theory. So I need to interpret this in such a way where it does have energy 5. Okay, so how do I do that? We can pretend as if particles already come with an energy. So we're going to rethink about why this has energy 1. Particles already come with 1 energy, but it's in its ground state, so it has 1 energy. This particle is in its first excitation state, but it has 1 energy within itself. In fact, that's what Einstein said. He said mass is the same as energy, E equals mc squared. So particles already come with energy. Okay, so does this work now? So this is in the ground state, but it counts for 1 energy. This has 1 energy as well, but it's in the third state. 1 plus 1 plus 3 is 5. Okay, hopefully I get 6 for this one, and then I know my theory's right. So let's have a look what the energy would be. There's 1 particle here that has 1 energy, another particle here that's 2 energy. This is in the ground state, so that comes with 0 energy for this one. This one is in the fourth state, so that comes with 4. 1 plus 1 plus 4 is 6. Okay, it's looking good, and I should get 7 for this. Okay, 2 particles, so this comes with 1 energy. This comes with 1 energy. This is in the first excited state, so it comes with 1 energy. This is in the fourth state, so it comes with 4 energy. 1 plus 1 plus 1 plus 4 is 7. Okay. You can do it with this as well, and you can check it works. You can do it with the next one if you want to write out the 6 poems. You can check that my energy level interpretation is good. Hopefully it's good. It worked here, definitely. If someone
Wait,
wants
so
to
what
dispute me,
you're
I'll feel
saying
free.
is that every line is actually a particle, and it can be in either a ground state or an excited state?
100%. And also
Like,
what I'm saying as well is particles come with a default state of 1 energy. And if they are in a more excited state, they come with an extra energy. Okay. Now, yeah, there might be other ways to interpret this, but I'm pretty confident that if you did it for 6, the same interpretation would work, and you'd get all these states. Why is this interesting? This is 6, the quantum version of 6. The quantum 6 is, bear in mind, because this would count as 1, this is q squared, q cubed, q to the 4, q to the 5, q to the 6, q to the 7, and that's exactly what quantum 6 is. Okay. Sorry, I meant quantum 8. Quantum 8 because there are 8 poems. Okay. So now we're not just counting poems, we're counting poems, but we're discriminating against them by coming up with some sort of physical interpretation where the longer syllables are somehow particles and have energies. It's really weird, but it's useful. And actually, this is going back to what Jen said. Jen said that there's a recursion here. This is a recursive number system. Yeah, it is. So this is how the normal Fibonacci numbers are defined. So we can interpret this. It says the next Fibonacci number is the sum of the 2 previous Fibonacci numbers. I believe that we have a very similar thing happening here as well. And I believe it's going to be this. That might be a -1 actually. This is a -2 or a -1 just by computing a few examples and seeing if this recursion works. It wouldn't be that hard for me to prove, but let's just not waste too much time on it. Okay.
Yeah, there's a question
terms
as
of one
to
last thing-
how much can recursion be coherent. So how much longer is this example going to go for? Because I feel like most people aren't following at this point.
Yeah, this example's just wrapped it up here. So I was going to move on. So what was the question?
Feel it in your leg if your leg is gone.
Excuse me, we're in the middle of a serious lecture here. Thank you, whoever.
What was the
muted
question,
me.
Jen?
I can start with my general questions now. Can we do that? You're done your examples?
How about we just wrap this up very quickly then? So
Oh, sure.
let's just have a quick recap of what we've done. It's kind of weird, okay? There's a metaphor that's going on throughout this whole thing, though. Take something that you're familiar with, something that counts things. Look at those things that you're counting more carefully, and see if you can make a further discrimination, right? We counted permutations before. Could we make a further discrimination? Yes, we could. We could also consider the number of swaps it took to get to that configuration. Okay, that's kind of like the energy of the permutation. We were counting paths here. Okay, we could count the number of paths. There were 10 paths to get from the bottom left corner to the top right corner. But we could count them with a further discrimination and count the energy of a path. It's the number of blocks underneath the path. So this one had energy 3, this one had energy 3. Exact same story here. We're counting the number of poems. That's what Fibonacci numbers count. But we can count with a further discrimination. We can treat these as if they're particles and as if they're in energy levels. I do have one more example. I'm going to go for it really quickly, and it might just absolutely be a bunch of nonsense because it's the most complicated example. Is there any more gentle questions before I just quickly rush through a bunch of...
I just have to say that it's not a question, but it's more like a comment. There is the Pauli exclusion principle that doesn't allow for like two fermions to be in the same state. You have something similar. You have two particles, and like every pair of particles, they have to be in different energy levels.
In fact, my next example, this is perfect segue. My next example literally is based on the Pauli exclusion principle. So let me just grab it. I put it way up here. Okay. So you can already see it looks tremendously scary. Let me just bring it down. Okay.
Those of you who don't know about the Pauli exclusion principle, the most readily available example is the periodic table. So there's no elements between hydrogen and helium. Why? Pauli exclusion principle. There's one per state. Hopefully that makes it clear. There's no intermediaries between hydrogen and helium.
Okay. So yeah, what is this gibberish? There's a lot going on here, and I will break it down, okay? So this term here that we have here, this is going to relate to the number of ways to split something up, okay? Kind of like, well, we'll see in a second. This term here is related to particles, so this is the particle term. And this term here, this is the antiparticle term. And this term here, these are the ground states of the particles. Okay. It's kind of weird to understand. So this wasn't my idea. I didn't come up with this. This was done by Richard Borges. He's got a great YouTube channel if you Google his name, Richard Borges. He teaches really, really complicated mathematics. But he came up with this proof. And well, what even is this formula? Who cares about this weird formula with like Q's and Z's in it and all sorts of crap? Well, mathematicians about 200 years ago, in fact, Euler really, really cared about this. Jacobi really, really cared about this. This is called the Jacobi triple product formula. And essentially, well, I don't know enough about it, but it relates to modular forms and modular functions, which is really, really high level mathematics. In fact, this sort of stuff you need in order to prove Fermat's last theorem, which is a nice theorem. So But what's really interesting is Jacobi's proof of it. He wasn't thinking about quantum mechanics or anything like that. He was thinking about weird functions. And his proof was horrendous. Whereas this proof, it is literally half a page long, if that, okay? I'm going to give you a rough sketch of the proof. So it goes like this. What we're going to do is we're going to take this term to the other side of the equation. And then we're going to consider both sides of the equation and show that they're the same thing. If I spend more than 7 minutes on this, please stop me, because I don't want to just be talking gibberish, because it is quite complicated. But let's just look at the left-hand side. So the left-hand side, we have this. We have this term, and we have this term. And I'm going to give you a picture proof of what this is. Now, why are these n minus a halves and n minus a halves here? It's kind of like weird. Like, why would a half appear? Actually, this comes into quantum mechanics. So if you've seen the quantum harmonic oscillator before, the quantum harmonic oscillator is a quantum system, but what's fascinating about it is the energy of that system. They come in half integers. So the lowest energy of a quantum harmonic oscillator is a half. Actually, it's h bar over 2. Omega, maybe. But I just set those constants to 1, so I'm going to say it's half. Then the next energy is 3 over 2, and 5 over 2, and so on. Okay, so I can actually draw this. Let me just, I drew it out already. Okay, so we're going to draw a quantum system. There is no such thing as a particle in this particular system having 0 energy. The lowest energy a particle can have is a half. So you can kind of think of this as a number line, and we can put particles on it. For example, this is a half. Okay, so if I look at this system, we have one particle with energy a half. I could put a particle here as well. This actually has energy a half as well. Turns out if I put it on the left, these are going to be antiparticles. Okay, so you can imagine this system has one particle and one antiparticle. And we can add the total number of energy of the system. The total energy of this system is 1. Turns out antiparticles don't have negative energy. In the way I'm modeling it, they also have positive energy. So the total energy of the system is 1. Okay, so where's the Pauli exclusion principle coming in? It actually comes in with these two terms. So let's just look at this term. Okay, so the Z here represents the particle. This represents the energy that the particle is in. So, but what's interesting is it's taking the product over different ends. So essentially what it's doing is it's saying no particle can have the same energy. For example, I could have another particle maybe here with energy 5 over 2, but I can never have two particles in the same energy state. I can never have two antiparticles in the same energy state. All the particles need to be in different positions. And that's related to the partition function here. Okay. So that's the left-hand side of the inequality. It represents this picture of particles and antiparticles. So if I just look at this picture, how many particles are there? You might want to say that there are 3 particles here. But if you know about antimatter and matter, they cancel each other out. In fact, there's 1 particle here. I know it looks like there's 3, but there's actually 1. You can think of these 2 particles as kind of negating each other in terms of particle number. So the particle number of this configuration is 1, and the total energy of this system is 7 over 2 if you add these fractions. Okay, so that's the left-hand side. Turns out the right-hand side is literally the same, which it should be. It's an equation, right? So let's look at it. We have this, and then we have, if I take this to the other side, I have to divide by it. So it's going to be 1 over the product of 1 over q to the n. If anybody knows about combinatorics, they might have seen this before. This is called the partition function. It basically is the product of all the different ways to represent a number. And so what you can think of this as is this is a particle system in its ground state, and you can think of this as an excitation of that ground system. And so the equation is kind of trivial if you interpret it like that. So left-hand side is the Pauli exclusion principle, saying consider all systems of particles where no two particles can be in the same state. And the left-hand side is saying the exact same thing. It's saying consider particles to be in their ground state and then excite them. Well, of course, that's the same thing. All the ways you can get to all configurations is obviously all configurations from the ground state that are being excited. And so that's the proof of the equation. I can go into more detail, and it gets more exciting when you look at the more details, but I won't be able to do that here. So in terms of that, I would like to get a bit more philosophical and a bit less pretentious now, because this is the height of the pretentiousness. Has anyone got any down-to-earth questions or any questions about this?
I don't know if you have time to answer this, but I didn't quite
I've got
understand.
a bunch of questions, but we still have about 70 minutes that we can go before the next event here. So how long you want to go? Did you just have one question?
I don't mind talking for a
Vortigern?
long time. Yeah, go on, Vortigern, what's the question?
I meant Vortigern, sorry.
Yeah, I don't quite understand why the 1 over 1 minus q to the n is there.
Yeah, so that's the bit I didn't explain properly. So this is the partition function. If you've seen this before, just very quickly, I know Vortigern knows a bit more maths than the average person, so I'm going to explain this quickly for him. If you look at this is a product over all n, and you can expand each one of these out as a geometric sum, right? So for n equals 1, you get this. Then for n equals 2, we're also timesing by this. Right? And then for n equals 3, we have this, and so on. And then we've got an infinite amount of these in this product. And this just represents the sum of p of n, right? It's the partition function. Now, like, what is this factor actually doing? It's actually exciting the ground states. So I'm going to do one example for you, and it also might be a bit confusing. If after this stream you want to ask me more about it, I'm happy to explain that in one-on-one. But I'll give you one quick example. Okay, let's say we have a particle in its ground state. Ground states are, here we go. We've got 3 particles in its lowest state. That's a half, 3 over 2, 5 over 2, right? And actually, that's where this comes from if you look. Because what's the sum of this? It's going to be the sum of the odd numbers over 2. And you might have seen before that the sum of the odd numbers is n squared. So that's what that is. That's the energy of the ground state. And then what is this doing? This is going to be an excitation. So this is how it works. What you do is you draw the ground state. So
This is not philosophical. Let's wrap
this
this
is
up.
not a philosophical question. Yeah, so okay. It's going to get a bit bogus, but what you have to do is you draw the partition out. So let's find a partition. 3 plus 2 is a partition. So you draw that out. And then you stick this on the front of it in a triangle. Sorry, actually, I drew it the wrong way. It should be like that. And then you can stick this on the front. Essentially, what's happening here is this is the ground state, and this is the partition. And when you combine them together, which is what the product's doing, it creates an excitation, and it creates a new configuration. And you can read the configuration off by sticking these two shapes together. I'll show you in more detail after the
So
lecture
ground
starts.
state
Okay,
plus
that's-
partition equals what?
Ground state combined with the partition
Okay.
allows you to get any configuration,
So
other
gives
words-
any configuration. Okay, cool.
which is the Pauli exclusion principle. So if I wrote it in
Oh,
English,
whoa. That's not the Pauli exclusion principle. It's something to do with combinatorics. Clear it all to me at this point how that relates back to the Pauli exclusion principle, but we can get to that in a bit. Can I proceed with my questions now?
yes, you may.
So it seems like this builds in Fourier transform type thing, Maclaurin series Taylor polynomial. Did you take any of that in building this?
Yeah, so the general theory, this is historically how it came about through that. In terms of like what we're doing here, that's exactly what this equation is related to. It's related to that sort of stuff. But what the beauty of this though is that's quite complicated mathematics, whereas just like messing around with pictures is nice and simple. And so you can circumvent all that Okay, and the Q stands for quantum. So I call it quantum numbers, whereas they just call it Q for some reason.
Okay, so this isn't like when you see the, because I'm looking at the Wikipedia article on it right now. So when
Yep.
you're saying it's a generalization of numbers, which set of numbers?
Natural numbers mainly, but more than that, like literally anything you can generalize. So just it generalizes exponential functions, trigonometry functions. It generalizes derivatives, factorials, zeta functions, gamma functions, binomial coefficients, factorials, literally everything you can think of.
Okay, so
and-
in the widest sense, is it a generalization of complex numbers?
I
'Cause the
saw a
complex
diagram that
numbers would
someone.
include all
Not
that.
in any way, shape, or form. That question doesn't even make sense.
Yeah, so I read a document where someone tried to explain this. It's not. If you think of generalizations of numbers, right, they're typically in the forward direction, right? Like you have the natural numbers, and then you have the integers, and then you go forward from that, and you have the rational numbers.
Mhm.
Right, you get fractions, and then what can you do with fractions? Well, you have real numbers like square roots and pi, and then you have complex numbers,
Right.
And we can keep going. We've got h,
Yeah.
whatever that means. Okay, so this is kind of like a weird cousin. You're not going forward, you're kind of going sideways. Like it is a bigger generalization. Or maybe
Gotcha,
it might be good to draw it up. So we could do it like this. Okay. Also, there's different generalizations of real numbers as well. So what's kind of interesting, there's this thing called the p-adic numbers.
Right.
So, and what's interesting is there's a quantum p-adic numbers as well, right? So any number system you can have, there's always going to be like some quantum things that you can generalize. So it's kind of like a cousin rather than like a father.
Okay. All right, that's all I was wondering.
But yeah, I mean, we've been focusing on numbers today, but it's not really about numbers. This is
Not
more
about
like
numbers at all. It's about boundary interactions and how to model them, and essentially how to go from micro to macro, right? And it seems like what you're trying to do is build something non-trivial into the number system. You've identified some issues with the current way we understand numbers. This is one step in the direction of fixing some of those issues. Would that be fair?
That's 100% what's going on. Yeah, it is. So the point is, the number systems that we currently have, they aren't sufficient because they're too simplistic. It's like a caveman invented them because a caveman invented them, right? We need a more sophisticated number system that somehow keeps track of states better. And the quantum numbers keep track of states better than the regular numbers.
Right.
They have more utility.
So I mean, it's not like it's not like they're better in some vague sense. It's that they're more accurate to use, like in the context of physics. But they should also be studied mathematically in their own right, as well.
In fact, yeah, they were first studied mathematically in their own right, and then physicists like looked over the mathematician, showed them, went, hey, we could do some of those.
Oh, nice.
So if you look on the Wikipedia page, there's some examples at the bottom of where
what do you think some of the problems have been with people studying mathematical objects in their own right, historically?
What do you think about that, Jen?
I wanted to know what you thought. I think everyone already knows what I think, is that it's got to be grounded in physics. Otherwise, it's really can't be established as much. But, to hear your
I think
thoughts.
it's the other way around. Go ahead, Euler.
It's Euler's stage.
It depends on the day you ask me what I'm going to think, but I think I have been brainwashed to think that you should be doing things in their own right. But what surprises me is that every time that somebody's been doing stuff in their own right, it somehow comes back around to physics. I used to not like physics that much, but when I realized that there's a lot of structure and beauty with physics, and it's not that far away from mathematics, it kind of like surprising.
Yeah.
So the big question is mathematics so like physics because like we're like inside the world, and so like any mathematical system that we come up with is somehow inspired by reality, like space-time, right? Like we have a notion of geometry. Well, it's clearly inspired by space, right? We have a notion of
Right.
like sequential numbers. Well, maybe that was inspired by time, right? So
In the Kantian way, yeah.
Could you please mute yourself, Steph? I'm asking the questions now, thanks.
so that's one answer, right? Like maybe because we're in reality, we can't help but come up with mathematics that somehow reflects back reality. I find that quite plausible. There's another thing that I've been thinking about as well, though, which is that maybe it just doesn't matter. Maybe like you could put a man
Obviously
in a
matters.
cave.
Look at what we're talking about. It's like literally all anyone can talk about. Everything is just reducing back to the same single question that you're alluding to here.
But maybe we're attributing it to different things. So we could
It's
attribute
accounting for the success of science, essentially, namely physics.
exactly. And how must we account for that? So we could account for it because we're just born into the world, therefore any system that we come up with it somehow describes the world accurately. Or maybe mathematics is just so absolutely powerful that you could just come up with a random system and it somehow is powerful enough linguistically, like it's got enough structure in it to describe anything. I am more leaning towards the first thing, but I keep in the back of my mind the second thing. Maybe just mathematics is so powerful that any system of mathematics has descriptive power.
And it's like, why is math so powerful? Like, you're not actually answering by saying it's powerful. What does it even mean? You're essentially saying brute forcing works. I don't disagree.
Yeah, that's right.
Why?
Yeah. Yeah.
I'm going to give a thorough accounting for why brute forcing works, not just make all these wishful thinking assertions about language and math and what precedes what. You said calculus comes out as a particular case of this. I'd really like to see that derived, because to me they don't seem compatible just off the bat. There seems to be something intrinsic to Euclideanism that calculus necessitates. If you can summarize quickly how you get around that. You did say you define a derivative, an integral operator, yes? What sense are those? Still what I think they are.
Can you rephrase the question?
I'm just remembering from my notes that you said all the existing limits. You said that you can define derivative operator, quantum derivative operator, right?
Yeah. Okay. I'll quickly touch on that. Also, I want to mention something you said before, because you said it's to do with like limits as in scale, right? Like quantum is about like small, but there's like we want a relationship between like the small and the big, the micro and the macro. And this number system is better tied into that. And this comes back to what I was saying before. You can maybe think of like the regular number system as like the macro. Like why should I think of it like that? It's because we walk around and it's like just like numbers. There's objects. We can count 2 objects. And the quantum system, it has an inbuilt way to recover back the macro. This is complete analogy. You can think it's hogwash if you like, but the whole point is, given
You're saying
any
the
quantum
quantum
system,
transcends scale, basically, just to be clear on this.
exactly,
Quantum
and
model.
it has
So
a
what does
way
it mean
to
for something
recover
to be
back.
modeled quantum mechanically, though? Got to be clear on that. What does that mean? Is it being modeled as a single entity? Is it being modeled as a single boundary, a single circle? What is a quanta?
I don't know about that.
Really mathematical identity at this point. Is that correct?
Well, the point I'm trying to make here is that inbuilt into this number system is a way to recover the old number system, in the sense that we have an inbuilt Q into the quantum system. If we let Q equals 1, we recover back the old system. Okay, let me connect the 2 questions together, because you asked, what is the quantum derivative? How does that work? Let's just remind ourselves of what the normal derivative is. So the normal derivative looks like this. Okay. So this is called the fundamental identity of calculus.
This is going to be a big derivation. Let's not go into it. This looks like it's
No,
going to be a really
this is not a big
algebraic
derivation.
derivation.
No, this is the definition. So if you look at the definition,
No,
of
it's the
a
definition.
derivative,
I
this
know
is the
most people
definition
don't know
of a
the
derivative.
limit definition of a derivative, so I don't want to lose the majority of the audience here. We don't have all the time in the world to get through all these questions.
There's only 5 people here.
I have a bunch of questions.
Okay. Very quickly, just what the quantum version is. Essentially, you just remove the limit. So you can think of the quantum version as not computing the limit. In other words, the quantum version actually doesn't run into problems of infinity, because most of the pushback from mathematicians when calculus was being invented is, what is this whole crap of tending something towards zero or making something incredibly small? Isn't there some sort of boundary that you're pushing it? Maybe there isn't. You can't just make a number arbitrarily small. Maybe there's like some limit, some Planck scale or something. Well, the quantum derivative gets around that because it literally just is the same thing, apart from you don't resolve the limit. The thing works, as you said, Jen, at every scale. You're not resolving the limit, looking at what happens when it's really small. You're leaving it unlimited, meaning it works at every scale. And then if you so wish, if you really want to, you can then recover back the original derivative by taking the limit, but you don't have to. In fact, you lose information by doing that. So very quickly,
Can we derive
the
calculus without the usual limit approach?
Oh, that's a really good question.
Because it seems like if you can derive polynomials and derivatives are polynomials and all derivatives have been an expansion, then it's like, holy shit, does this thing allow us to do, like, it's almost like you solve the P equals NP problem without realizing it computationally. 5. Question from the audience. Define entropy in a multiverse, but go ahead and ignore that last word or those last 2 words if you'd like. To see how this may relate to entropy. I can give a potential answer, but if you want to go first, that's cool.
I don't have an answer to that, Jen, so I'm curious what your answer is.
What's entropy? What's K ln omega? What does that even mean? It's the number of microstates per macrostate. I mean, come on. That's the whole statistical mechanics. That's the notion of statistical mechanics, is that essentially that there's a distribution of possible energies, and there is a minimum energy, but it doesn't have all the particles in it.
I just got maybe a simpler question.
I'm not done.
Euler wrote here.
I am really tired of being interrupted by you, man. I'm really happy that you're here, but I'm not done. And this is extremely technically difficult material. Please mute until I'm done. A way to count the microstates. So something countably significant coming from what appears to be infinite data. That's where it gets real tricky. So I was thinking that you could present this as the solution to an existing problem. We've got the printing out infinity truths, right? Contradiction problem, which math already has built into it through the reals. Ironically, still can't get physics to work even though the math is cheating. It's quite hilarious. We're sort of in this spectrum between infinity equally meaningless statements. Slash, is infinite recursion really a problem? It's like, yes. You can never draw an actual conclusion. Yeah, it's kind of a problem. At the other end of that, we have way too restrictive of a system where it's just like nothing means anything, not going to name any names or anything. This is a model for reality. It's full of permutations. And what's the difference between a combination and a permutation, Euler?
That's a good question.
Is it that in a combination, the order does not matter, and in a permutation, it does? Therefore, if we can model the universe based on permutations, then we live in an ordered universe, and we may have, quote, demonstrated that. Whether that's a proof, I mean, have to accept that math is capable of modeling reality. That'll come from actually doing an inquiry into, is that a reasonable supposition? We're in the chicken and egg now. At least we've only got 4 things in the chicken and egg jostling around. That's better than infinity, but we still need to pin it down more, i.e. freeze the waveform in a crystal. We can break it down and make sense of it. Would you say
Here's an
that this is
idea.
more of a two-dimensional counting principle versus a one-dimensional counting principle that we're used to? So like I would say this is an awesome start, and I wonder how you feel about that analogy. Like the way we count right now is fundamentally in one dimension, even though they're quote unquote orthogonally built, are all the same one dimension. And what you're doing is counting in two dimensions.
Yeah, I really, really like that. In fact, I was thinking of a similar analogy to that. So there's actually generalizations of this number system where you have a Q and a T. For example, if someone wants to Google it, there are these things called the QT Catalan numbers. And it's it's a generalization. We've got two things which are doing the counting now. We're not just counting like the energy. There's like two different types of energy which we're counting. So I'd probably call this a two-dimensional number system. I don't know if you would call it three-dimensional. I'd say since there's just like one variable here, I'd probably call this a one-dimensional counting system, and I would maybe call the regular numbers a zero-dimensional counting system. So the regular numbers are zero-dimensional. I'd probably call the quantum numbers one-dimensional. But that's just my convention.
Would you say it's statistical deviations from 0-point energy? Without knowing what that means.
Deviations.
I mean aesthetically as a name, without having to commit to any particular definitions, if that sounds right-ish. Because that's how Thad describes his model. Again, ish.
Yeah, that's kind of related a little bit maybe to what I was doing here about how this is really zero energy right in the middle here. But you actually can't get zero energy. There's always a deviation from zero energy. Right, the lowest energy you can have is a half. And you can't actually quite reach the zero energy state.
Because the monad is unobservable. Just kidding.
Well, I don't know about that, but
Oh no, it's okay.
I'm
There's
not
plenty
sure
of
why.
time to learn about that.
It's a mystery for me. Yeah.
Does this generalize to Brownian motion? I would challenge you to try to get Brownian motion out of this as an example. And if you can't solve it, let me know how far you get, and I can take a crack at it with you if you feel like it. I had a joke, which is your path is sad, brah. That was just another note that I made. I just don't want to be interrupted, goddammit. Mute yourselves and I'll tell you when you can unmute. Like, honestly, what's going on here? This is my stream. The name, respect the name.
We respect it, Jen. Okay.
Certainly don't push back on what I'm saying here. All right, so I guess we can let the other people ask some questions now, and I'll mute. And yeah, looking forward to the next chance to answer a question from the chat. Hope everyone's enjoying this as much as I am.
Do you have a question, Vortigon?
Yeah, it's actually way back with the Pauli exclusion principle. I still haven't quite understood how it relates to what's going on here.
In the picture here, we're looking at different states, right? So here there's like 3 particles. The configuration has a particle number of 1. But I'm not counting states where there's 2 particles in the same state. That just isn't a configuration that's even possible. So the reason why it's related to the Pauli exclusion principle is the only states which can exist in this quantum system are ones where the particles are in different configurations. For example, we have a particle here in state 1/2, with energy state 1/2. We have a particle here with energy state 5/2. They're not in the same state. We can't have 2 particles with energy 1/2. We are, however, allowed 1 particle with energy 1/2 here and 1/2 here because one's an antiparticle and one's a particle. They're not actually the same state. So although these look like they're in the same configuration, they're not, because this is an antiparticle.
It kind of reminds me how like if you have electrons which have spin half, then the dimension of the spin space is 2. So you can have like 2 electrons in a ground state, which is exactly what you have here. So you can think of the particle and antiparticle pairs as spin up and spin down pairs. Like
Yeah,
it's
exactly.
kind of...
So I was thinking about this as well. It's about creating analogies, right? Like, what's gonna be a more fruitful analogy? Do we want the Z to represent spin, or do we want the Z to represent particle antiparticle? And what's kind of interesting about this is like a way for us to generalize the system. Okay, because we've got 2 approaches to generalize it. We can interpret the Z as particles, or we can interpret it as spin. Well, why not have a four-way system where we have another axis here, where we have sort of like, how would you call it? Particle anti-particleness. So particleness along here, and we have like spinness along here, right? And then you've got like a square grid of possible energy states. And there's going to be an analogous equation like this. In fact, I'm going to spend some time 1 week probably finding the generalizations of these equations by adding extra axes, because this is just a one-dimensional quantum system, but obviously you can increase that.
I see.
And this is where like the QT Catalan numbers come in. Things like this. There's two different flavors going on, right? We could have Zs in as well.
It seems really nice, but what if you take like, I don't know how analogous it is to quantum mechanics, but what if you take some realistic system like the hydrogen atom? It has 3 quantum numbers. If you add like Qt and I don't know, V or something, can you get something similar to the hydrogen atom?
Yeah. This is my conjecture. So the conjecture is this: simple quantum systems, and simple being ones that you can like actually compute, like the hydrogen atom. They have the reason why they exist is because there's like mathematics as either describing it or restricting it. There's only a certain number of symmetries which can even occur. Is it a coincidence that the quantum harmonic oscillator, the simplest quantum system, has such a lovely structure? Well, no, because there isn't really much room for it to be anything bizarre. And it's the same with the hydrogen atom as well. There aren't many mathematical structures with a lot of symmetry. And so what you can do is you can look around at mathematics, find these structures, and correspond them to quantum systems. And every time you do that, there'll be a little dictionary, a little equation, which relates the quantum system to the mathematical structure. And you can
Why
get an
do the
equation like this.
structures
That's my
need
conjecture.
symmetry?
Why do the structures need symmetry?
This is what I actually thought we were going to be talking about, is building up the quantum mechanical understanding, theoretically, from the periodic table. I thought you wanted to talk about is the justification of quantum numbers via the periodic table. Now the math kind of came second to the necessity of quantizing and understanding there.
The thing is, I don't fully understand it. So this is just me making a conjecture, and it's not an unreasonable conjecture because Vortigern's thinking the exact same thing. Why can't we look at other quantum systems and see if there's more symmetry, more structure going on? So if I can link a paper to explain what I mean. But this is related to the Jacobi triple product formula. There's this other one, I think it's called the
How are you going to
Macdonald's.
tell that the symmetry is a property of physics or math?
That's a good question.
At this stage, there's no way to tell. I'll save you the trouble. It's all just working because of brute force. That's the default hypothesis. Force. That's why it works. Brute force
is
and a
that what you think then?
computational limit. The universe has a computational limit. A Greek era thought processes to derive that. Math has no bearing
The way I think about it is like,
in reality. I'm not saying that is true. I'm saying that should be your default position, and then go from there. If you have other evidence that would sort of deviate you from that initial position.
yeah, and I think actually, if the conjecture is true, that for every quantum system, we have a corresponding like mathematical description of it in this way, that does sort of suggest a very, very deep relationship between mathematics and physics. That it's not just random, but there's like some relationship that's got to do with symmetry. In fact, it's related to polygons. So
Like back in the day, they understood right angles as a thing that was conserved. I don't know if you ever saw that article about Pythagoreans. Angles.
Right angles being conserved in what way?
Grab the article. I don't want to start guessing what it said. Just keep going. If anyone has questions, I saw someone else join. I'm sorry I was cranky earlier. I just really passionate about this stuff, but please go ahead with your questions.
Oh, by the way, another like last thing. What's really exciting here is if the conjunction you mentioned is true, then maybe, just maybe, we can arrive at conclusions regarding the helium atom. Now, the helium atom is not solvable analytically. What if you can actually derive some of the properties of the helium atom combinatorically? Like this. And like
Yeah.
obviously much more complicated system, but
Yeah,
what
dude,
if you
that's the whole point of this discourse. It's awesome. We already can do it. And by we,
I was
I
gonna
mean
ask
me.
I was gonna ask a question about what you were saying about the definition of a derivative in this quantum number system.
Yeah. Okay, here.
Yeah. Okay. So you're saying there's no like with what you wrote there above with the how it's usually written, but then you omit the limit,
Yeah.
the notation for the limit.
So I'll write it like this.
That's actually
Okay.
not what he said. He said that we don't even have limits anymore because the zero concept is integrated so seamlessly. Wait, is that actually what you said though? Hang on.
Yeah, we don't have the quantum version of the derivative doesn't have a limit in it. Okay.
Okay.
So the way we recover back
It does
the
have a
limit,
limit, you just can't recognize it as a limit. Something is serving as a limit. If you can derive calculus, it has something computationally equivalent to a limit in it already, right? That's the way you gotta look at it.
Yeah,
Black
literally
box
that.
it.
So it's more. This is more general than the normal derivative, and inside of it, you can think of there as being a limit inside of it. But the thing is, this is way nicer to work with
Okay.
it, and you can prove computationally. Like what Jen was saying earlier, you can actually derive a lot of the results from calculus, like the product rule, the quotient rule, the chain rule, strictly using
Okay.
this. The chain rule is a bit of an awkward one, but and you don't have to prove it
Dude,
using limits at all.
integration by parts is the hard one. What are you saying? The chain rule? No, I get it. I see why that's hard. Never mind. Self-reference, yo.
Yeah, and there is actually, as Jen said, there's a quantum integral as well. I actually haven't looked at the quantum integral myself. I've seen it on Wikipedia, but I don't know how the formula looks.
So there's like no occasion here like where like if you had like let's say the qx minus x equaling 0.
No, because the q here is a formal variable, right? So it's not like a number.
Okay.
The q here isn't a number. So you can think of it as like a polynomial, right? So this thing could never be 0 because this could never be the 0 polynomial.
Okay. All right. Okay.
Oh, another question. Is that related to like when you talk about polynomials, that kind of reminds me of ring theory and modules. Is that related to abstract algebra in some interesting way?
Yeah, so if you want to define this rigorously, you have to talk about like a formal power series, and formal power series involves ring theory. The point is, it's like so intuitive though. Like, there's no point going all pretentious talking about ring theory, because the whole subject of formal power series was invented by Euler way before ring theory was, right? So although he didn't have like the rigor behind it to back him up, it doesn't matter. So this is kind of obvious to understand. It's just a thing divided by another thing. You can talk about it in formal terms, but there's no point.
All right. Thanks for answering my question. All right. Yeah, I haven't heard about this stuff about quantum numbers or anything like that. It's
Yeah.
all neat.
There is actually connections to algebraic geometry and ring theory though, and field theory. So I haven't proven this to myself. It's on my to prove list, but the quantum binomial coefficient counts the number of subspaces in finite fields of dimension k. And like where the finite field where q is a prime number. I have no idea how to prove that, by the way. But
You accept the measurement limit, you
finite
can
field.
prove a lot of things computationally. Take the principle that 4 waveforms can generate 118 microstates. It's a general principle. It's the informational limit of the universe.
Do you think that the periodic table is complete, Jen, or do you think there's more stuff that we haven't seen yet?
I predict it's complete at 118. It's not everything in the universe. Obviously, it's just one trace of All-Father.
What's lovely about this type of mathematics is you encounter lots of structures which are complete. Like a lot of the times, things just keep going on forever. Prime numbers, they just keep going on forever. There's an infinite amount of them. But more combinatorial things, there's a finite number of them. There's a finite number of platonic solids. There's just 5 of them. There's no more than that. You could never find another one.
4 gives, it's not solids, it's elements. So it's 4 gives 118. So you're looking at a dilution factor. So if to go from 4 to 118, somewhere that in there is the dilution factor, transcends all the orders of matter. The idea is that we're looking at the same information from different angles that we're looking at the periodic table. That didn't come out right. Sorry. Because somebody was asking in the chat about entropy, and to me it's self-evident, but you didn't spend many years studying math. Trying to kind of go between 2 problems of way too simple to be meaningless, of like tautologically trivial stuff that, like, I think example that Euler gave was the simple harmonic oscillator. Well, yeah, everything admits that decomposition. It doesn't make the decomposition correct. It means that it's so general that, you know, we have to sort of ask, are these concepts falsifiable? Are they just so general that they're brute force?
Yeah.
Entropy is about accounting for sort of the one and the many. Like, how do you get what appears to be 118 from 4 on all scales? So how do we get, you know, all these different words, even though there's really not that many concepts and all these other things like that? Go ahead.
Whether this sort of thing is empirically viable, whether we can actually test it, if it's falsifiable or not, is an interesting question. So, I mean, Vortigern brought up the point, like, maybe we can actually learn stuff about different atoms by looking at structures. And maybe this might be a way to actually prove that there is only a finite number of atoms of different materials. So just like we can mathematically prove that there's only a finite number of elements, if we somehow find out that there's only a finite number of other types of symmetries, these type of combinatorial symmetries, that could prove that there's only a finite number of atoms, because there's only a finite number of quantum systems.
We use the fact that we reasonably presume that there's a finite number of atoms based on the fact that we can hardly even get anything to 118. We can just establish a trace of energy can be deposited there. We can't have any, like, we haven't established a stable system at 118. Then we use that to extrapolate a more general counting principle for all levels of resolvability.
Yeah, and I guess this would be like a different way to show it then, right? Like
you just use the principle. You don't need to prove the principle. The periodic table proves the principle, and then you become a person who applies that counting principle. Extremely difficult to do. Is visualizing 4 dimensions coming from 1 and 2-dimensional thinking is not easy.
Don't you think it would be beneficial to have like a way to prove that there's like wait, do you think it's possible to prove that there is only 118 atoms, different elements?
If you accept the axioms, yes, I can prove it, but proof always comes down to accepting axioms.
Yeah.
I think the axioms that establish that are reasonable. We already have a lot that suggests infinity is not really something possible. There's Zeno's paradox, Pauli exclusion principle, and that all sort of hints to it. I think. I'm sort of alluding to a burden of proof type question also. But the way I want to approach it is seamless integration with what's already there. So an ability to, based on axioms, derive proofs. The axiom in some sense would be that I gave you my like working list, but that's obviously subject to change. It would integrate the information from the measurement limit, aka this 1, 2, 3, 4 type orthogonal counting principle. It has something to do with the information, like the relative amount of permutations between 4 and 118 as a transcendent principle.
Yeah, so maybe if from your axioms or anyone's axioms, hopefully they're reasonable, but from them, maybe you can figure out from them the total number of possible symmetries that there could even be, and then actually show concretely, this is the total number of atoms that there could ever be. There's not going to be any more because there aren't any more symmetries for them to even be. And
The
that could
idea
be
is
wrong. 'Cause maybe
to
the atoms are
use
one.
as few suppositions as possible. You want your proof to be as simple as possible, and that comes from having as few suppositions as possible, and the suppositions themselves being also structurally as simple as possible. That's why there's Kutov, I don't know how to pronounce his name there, but he's saying all the stuff that, that's accounting for the success of the circle as a fundamental, what we call metaphysical primitive, is computationally equivalent to a boundary, which is the simplest way you could make a distinction between two things, conceptually.
Is the distinction like the inside and the outside of the circle, or what's?
You got it, dead on. That's the definition. And what's inside and outside? And you have that asterisk where you fall into the black hole of topology. You just hope to the almighty no one asks that question. Keep your fingers crossed for all time. Just kidding.
Well, and speaking of topology, that just very quickly, there is one last example. I was going to show it, but I didn't want to. I'm not going to show it. I'm just going to talk about it. But this quantum combinatorics, it also relates to quantum topology as well. One interesting thing is knot theory. And in fact, this relates to particles. Back in the day, when people would come up with theories of atoms, they thought that maybe the periodic table corresponds exactly to the number of knots. So let's just draw a few knots. Right? The first knot that you can draw is the circle. It's the unknot. In fact, all knots are circles, but they're tied up in different ways. I don't know if I can draw this.
Circles or a cylinder tied into itself. My understanding was that it was a straw feeding into itself in the shape of a circle.
That's right. Yeah, like this. So
We
this
really
is the
need to
trefoil knot.
that aspect of it is the most important thing. That's what most people miss. You could literally just focus on that subtle distinction. The question of where's the inside and the outside, well, that's how you deal with limits in this system, is when you swap them. It's like, when can I switch inside for this? I was like, hello. Somebody say transcend the space-time continuum.
I'm not very good at knot theory. I'm terrible at drawing them, as you can see. But
Well, luckily, the
there's
universe
a bunch-
can't count higher than 4, so it doesn't really define, there's nothing defined past HF8 and its complement. There's that.
I'll try and draw the next one, but I can't. So I'm not going to. But yeah, I could draw one more, maybe. So this is the first one, the circle. This is the trefoil knot. This the figure 8, which I can't draw. But I think it was who was it? Maybe Kelvin. I don't know if I'm making that up. Someone fact check me. But I think Kelvin, he was like, it must be true that the atoms correspond to ways to tie up knots in three-dimensional space.
It must, I mean, obviously.
Well, yeah, people bought into it for a while, and then I don't know, they kind of like poo-pooed the idea. Weirdly enough, like physics always does a full circle, and like the string theorist crew, they're kind of like looking back at his ideas and going, okay, I mean, he got it wrong, but maybe there's some truth to what he's saying. I know nothing about that. That's just what I've heard. But what's kind of interesting is mathematicians started looking at knots, and then Ed Witten. I would check out Ed Witten's interviews on YouTube if you haven't already, but he's an interesting
All right, well, let's
guy.
account for it. Why are people in love with knots? What do you think?
It's a really good question.
Is it a model for some physical process, perhaps? think, what would Professor Wolfram say right now? Does it not correspond to reality?
I like
Guess.
that because
I can give the answer, but you want to guess first? Anyone
well,
want?
I think I know what Wolfram idea on knots are. So he talks about like topological invariance, so like knotted up bits of space time, and he thinks that particles correspond to these sort of topological invariants, these like knotted up bits of space. And
Give you a hint,
there's, like,
okay? The knot. I'm gonna want to give you a hint here. The knot is scale invariant. It's non-localized.
Non-localized.
So imagine that shape getting bigger for all time. Pan-dimensional. The dimensions come out of it, not in it. Out of it. Knot is an entanglement model. This is not saying three things entangled.
As far as I understood, I thought there was a sense of scale with Wolfram's theory, at least. But Wolfram might not have everything right? So I think, though, in Wolfram's theory, the knots are localized because he wants them to correspond to
There's
localized
always going
particles.
to be, you have to learn to be able to get past just these binaries, is that, yes, there's an aspect of a knot that's always going to be localized. Of course. But the identity is not localized. See what I mean? How it is necessarily, like a sphere is necessarily localized because it's a boundary. Boundary is a localization.
So in what sense is it like non-local?
Has no preferred scale. Is the thing that makes the scale. To think that it has a size, even though it does mathematically, which is the amazing thing, that we can find a finite volume to the complement of the HF8. In some sense, the HF8 represents quantum state inclusion. 3D in the same place at once. It's impossible. Because of quantum state exclusion.
I think I know what you're
Because
talking
of
about
quantum
now.
state exclusion. Quantum state inclusion is impossible, which is the HF8. Everything other than quantum state inclusion is allowable. So what you have is a statistical, quote, simulation of all the states that aren't the limit point, aka the complement, the topological complement.
Yeah, so there is some sense in which the topological complement is scale invariant because you can define the volume
No,
of
it's not. The volume is like
complement.
1. How could it be scale invariant if the volume is 1? Whatever it is. Not 1, but you know what I mean.
My point is you can take any knot that looks visually different in scale and you'll get the same number if you calculate the volume.
Anyway, Euler, great talk. I'm glad you showed me quantum numbers. I didn't know about that. Thanks.
If you ever
See you
want to
later.
ask more questions about it, feel free. Take care.
All right, will do.
By the way, another thing, you define the quantum derivative. The Schrödinger equation has derivatives. What about the combinatorial Schrödinger equation?
Oh wow! See, you're brilliant. I've never thought of that. I've no idea. But I'm gonna explore
Because
that.
I really stretch it like far. In order to have something like this, you need to make like an almost perfect analogy between this and quantum mechanics. You need like you need at least.
No. In order for quantum mechanical theory to be right, it has to correspond to reality, aka experiment. Schrödinger equation does not correspond to reality, and it doesn't correspond to anything past hydrogen atom, as far as I understand.
Yeah, so we need at least an analog to a wave function here. So like,
no, you do not. The wave function is the analogy. Wave function is the analogy. You're saying you need an analogy. You need an analogy. Why?
Okay, I want to explore that for a second. So, the thing is,
just want to respond to someone in the chat real quick. Sorry. Knots computation would never end. Yeah, I know. Knot computation doesn't end. Time doesn't end. The whole point of the model was that you needed ongoing. So it's just do, good to go. Right back at you, Euler.
In terms of like how you'd come up with a Schrodinger equation for this, I don't know how you'd do it, but the solutions to it are going to have to be eigenstates.
Right question is, how do you model an electron with it? How do you model a proton? How do you model a free neutron? How do you model things with it? That's the question. Not how does it line up with the extant doctrines that explain one atom.
Well, I think me and Vorticon share the same sentiment, which is like, if you can describe one system with this model, and it works really, really lovely, really elegantly and simplistic, you just dream big, and you pray that maybe you can describe other systems with it. And so I get why
the
Vorticon's
Schrodinger equation is a description. Schrodinger equation is a description, though. Understand? That's not the thing your model has to correspond to. Reality is the thing your model has to correspond to. Specifically thermodynamics. I would say specifically look at thermodynamics because the framework's already there. And it's essentially the right presentation.
Yeah, I kind of see like the Schrodinger equation in this context of how we would use it to make predictions. Is we would.
Schrodinger equation doesn't make predictions.
I'm talking about mathematical predictions, not physical predictions. So
okay,
what we would do is we would come up with the Schrodinger equation based on this analogy, and then use the Schrodinger equation to come up with the analogous version of the quantum systems for like the hydrogen atom, by finding like the Q analog states of the hydrogen atom. There's something really interesting, because you said the helium atom can't be solved analytically.
I'll tell you one thing that was done. There is a way to approximate. It's like one of the ugliest things I've ever seen. You can approximate the energy level, the ground state of electrons in a helium atom with perturbation theory. Super ugly, and the result isn't even that close to reality, if I remember correctly. Like, no exact solution exists. There are like bad approximations.
I don't think this is going to like fix that issue though, because
yeah, but you know, I can hope.
It's going to make things worse, not better.
Yeah, I'm one of those people. I'm not willing
we
to
had
accept.
a few people join last minute. We only have like 15 minutes before the next event starts, and I don't want to have an event going at the same time as Nirvana does. So, Quantum, did you have a cue hop in with, or were you just listening in? Because also I see Kurt Cobain joined. Nice to see you both.
I just came in to see what was going on, honestly. I wasn't
Yeah.
What's up, Quantum?
Ain't not much, Kevin.
So
Okay. So
what's the next?
I'm happy to wrap this up. So we're currently doing a little mini lecture here.
You can still do 15 minutes. It's fine. The next event's starting in 15, so I'm cool to go right to the end.
Okay. Just to make people clear on the topic, I described a new number system. I say new, it's been around for like 300 years, but it's been recent is like the past 50 years, being used in physics to describe physical systems. And the point is, it seems like there's a close relationship between mathematical symmetries and actual physical quantum systems. And so this might be like a gateway to better describe quantum systems by using these things called Q numbers, or quantum numbers. But we're opening it up to a more philosophical chat right now. So if anyone's got any physics related questions or topics, feel free to bring it up.
I gotta love that, eh? Totally dead air. All right, let's recap. So the key thing here, where it becomes art as much as technique, is balance of keeping that you said at the beginning of your discourse. I don't know if you said dimensional information, but some kind of meaningful type expansion without trivializing it by creating what amounts to a truth explosion.
Yeah, this is a complete expansion of the number system. You're not losing anything. And like nothing bad happens when you do this. In fact, you get more beneficial things. For example, the quantum derivative, you don't have to take the limit, which is a huge benefit because you don't have mathematicians like N.J. Wildberger on your back saying infinities don't exist, please don't take limits. Right? Like N.J. Wildberger, in fact, does a lot of these things as well, where he deals with a thing called rational trigonometry.
I have to make a comment that technically, like now when I think about it, the definition of a limit doesn't explicitly include infinities.
It's essentially a geometric argument. At least that's how it was presented to me when I learned calculus, is the slope argument, almost trigonometry.
Yeah, and that's how N.J. Wildberger does it. So he just does it with like finite slopes, I think. I'm not really sure though. I'm interested, Vorticon, why do you say it doesn't involve a limit or like infinity?
Well, think of the definition, right? Like for example, well, like it involves a limit, but
I think you're saying you don't need infinity to define a limit.
I'm not into technical. Okay, actually, you do kind of use it. You do need infinite sequences, so yeah, you actually do need it. Like it. Maybe there is a way to avoid it because like first you define limits of sequences and then you define limits of functions, and the
dx is quantifiable, then yes, it is because of
the infinite stuff
principle.
they come into use when you talk about limits of sequences, and then they're like in the back of your mind, but when you define limits of functions, but they don't appear explicitly in the definition. So maybe there is a way to like get rid of infinity this way.
I don't
Yes,
know if
to-do
there is
list,
though.
divide by
Because think of epsilon delta definitions, right? Things are like less than or equal to 0, larger than 0, and you know things like that. No infinity involved in that part.
Yeah, the infinite is defining the infinite sequence. That's the
Yeah, but
infinite resolution.
it's kind of
though.
hidden.
Don't you need infinity? Don't you need actually, I think you need more than one concept of infinity. And to make a distinction between the large and the small infinity. That's obviously a concern if you want this to match with physics. Your large and small infinities cannot possibly be the same construct. Is that not, I mean, am I the only one who's made this, observation or what?
I'm trying to understand that point. So there are two different types of infinities going on when you're taking a limit.
Computationally, no. I mean, I understand Aleph naught and Aleph 1, that those are, quote, different. I get that. There's interoperability and there's no other real infinities that I'm aware of.
Yeah, and I think actually this is nice because this just kind of like scoops all the infinities under the rug, and if you want to like unpeel them, you can, if you wish, take the limit to q equals 1 to recover back limits. But just to prove my point, the whole thing that annoys people in calculus is the whole dy of dx, and they think it's a fraction when it's not a fraction. It's only when you get to like maybe PhD level where you start doing differential forms where you can start treating these things.
Come on, I did those in undergrad. I did those in second year.
Differential forms.
You
Well,
can do
you're a big
fucking.
brain.
You can
I
do
have
that
to
in
say
first
that's
year.
kind of correct. Yeah,
And you can
it's
cheat and do that shit in first year because it always works. The integral is defined as that essentially.
I don't think people do a
Problem
rigorous
is,
treatment of differential forms.
look,
until much later.
It
but-
inherits the same problem as Zeno's paradox. It can't possibly have a correspondence to reality until that issue is resolved. Infinity has to be that which does not possess a boundary. Cannot be that which is infinitely large, because that doesn't necessarily make sense.
Euler, I have to tell you about one forms that when I took vector calculus in my second year, it had one forms. So like, yeah, it's second year.
Oh, that's a pretty nice course then.
It was
I
nice.
teach second year multivariable calculus and vector calculus, and it's very rare for there to be differential forms. But I guess your country's awesome. Okay, so what's
When
nice
do
though
you
is
teach integration by parts? Isn't that tantamount to differential forms?
Oh, it's first year. You don't need one forms for that.
Just seems
so
equivalent to it. I mean, it's been a while, but whatever. Let's
No,
not get
no,
bogged
you're
down
right,
in
Jen.
minor pedantic digressions here.
No, you're right, Jen. Like integration, it secretly does involve differential forms, right? Like you have these things on their own.
I'm just imagining this like sneaky little differential form sneaking around in the shadows, be like,
Which is exactly what's going on. Like people just kind of like get confused why there's a dx here. Like what's it doing? It's just notation. This is kind of just notation. But the thing is, the whole why I'm even bringing these up is the whole undergraduate confusion about like differential forms. It goes away because the differential forms are like actually not that complicated. They're just expressions. So in general, we have this is going to be this, right? So this makes exact sense because look at what dx is. It's going to be this. And so look at the expression that I wrote above. It literally is a fraction. It's literally df of x over dx. And so the differential forms in quantum calculus truly do work like fractions, which is nice because you'd think if you make the number system more complicated by paying attention to more stuff, that things would get harder. But actually, a lot of things get easier. There's a few examples. I Googled some on Math Stack Exchange of examples where things have been easier to prove stuff using this number system rather than the regular number system. By making things more complicated, you make other things simpler. And so there's an example of plane partitions.
I call it information-rich primitives.
I would love a good name for this because I see it all the time where like there's like a conservation of complexity where you make something else harder and something else gets simpler. And I guess it's because it's got more expressive power. It can express ideas in simpler ways because it's got more ways to explain it. That makes sense.
I remember a lecturer who told us about it was a physics lecturer. He told us about the conservation of difficulty in physics.
How does that one work?
The same problem will always have the same amount of difficulty.
Conservation of complexity.
Kinda, yeah.
Here's the basic idea, okay? Like every interaction is something to the system. You're looking to line up your interferometer, which is interacting with the system to measure it, should minimally perturb your seen them. I want to see the notes.
It's very good. If you want to look at what
Kind of like, look, if you, it's the thing about lectures. If you listen to the lecture, then it doesn't really matter how messy it is. Like, your memory will fill in the gaps.
Yeah. And if you want, you can just rewatch the lecture, or because we're friends, you can just ask me if you want me to explain this, because this is honestly the cherry on top of all of it. But it's the most complicated thing, so I couldn't go into it in much detail here. Anyway, it's a lovely place to wrap up. Thank you, Jem, for hosting this. I always appreciate it.
Awesome. I'll just say to close up, next step, I'm going to look into this too. I don't know how far I'll get, but deriving calculus from the binomial expansion. Interested just to see how computationally complex that is, because to me, the point of math